Hello everyone. We have arrived to episode number 26. Thanks to Fabio Ciucci for letting me to stream his book. We have arrived, as you can see on your screen, we have arrived on chapter 8. We have finished chapter 7, which was about sprites and collision detection. And at the end of chapter 7, okay, you also saw the note that the book was divided in two, okay? So till chapter 7, okay, he wrote it and he released it in 1995, okay? So he wrote the book in 1994, to be honest, because it was in the beginning of 1995 when he released it. And then he started writing this part of the book after that. So this book was released, I think, in 1996 or a bit later. There are topics on the floppies that are not covered in the book. There are some more advanced topics which are not really, when you print the book, you will not get them. So I suggest that you look at them. Also, from today onwards, if you don't have the sources, you're going to struggle. So please go and download the sources of this book. It doesn't take much, okay? But having the sources in front of you is a must now. It's not, the sources are not anymore a simple few lines, okay? They are going to be quite complex. The other thing is this chapter 8, merges lots of things together. In fact, he says going deeper into the 68,000, okay? Getting to know it better. What he means is that there are topics that not necessarily are 68,000, which he will cover and you will need to know. The chapter starts by writing a startup file. We will not finish writing the startup file today. It's too long to finish it today. However, you will see that the startup file is quite complex, and he goes into quite some details to make sure that whatever we start, whenever we take control of the Amiga, everything works, whether we are using Kickstart 1.2 to Kickstart 3 or 3.1. So you need to, although the startup file, you will use it by calling your routine, and you will forget what it does. When you have issues, you'll need to know what it has done or what it is doing. So, and I can tell you that the startup file, actually I can show it to you in a minute. Is quite a long. This is the startup file. This is not complete, the startup file, okay? It's part of the main. There is a part which we will not cover today, which this routine that he calls. But we will cover all the rest that there is in this file. But before, if you recall, we always had some startup code and then some exit code, okay? So that we can take control of the Amiga. Now, that was a crude way of taking control of the Amiga. We are going to do it the proper way now. So the Amiga will not give us the famous guru that we are used to. Let's put it this way. It will be more robust and it will be more difficult to get, of course, guru from our startup file. Today we will not see the Amiga at all. We will not run any code. It was just theory. You will just see it in the right hand corner, lower right hand corner, just there, but it's just clicking the floppy drive. Let's put it this way. It's not doing anything else. We will be jumping to other stuff like on my whiteboard or on some or on the on the reference manuals of Commodore, the Commodore reference manuals for the Amiga, but we will not use the Amiga at all today. Probably not even next week. The examples are quite at a later stage. The startup file is quite long, and it is why I'm insisting that you download the sources and be able to follow using the sources now. So let's start with the startup file and what he says about the startup file. In this chapter, he starts by saying that first of all, I jumped the first page and page and a half because he's just saying how to install the sources on the hard drive. We have already covered this in episode number 1, so I do not need to repeat that. Since this is the second part of the book, which was, as I said, published at a later date. So here he says that, as we saw in chapter 7, okay, we were using a lot bit manipulation, okay, for manipulating the sprites. He says this will become even more heavily used in what we are going to do from now on. Also, some more, let's say, deep touch to the 68,000 instructions. We will go into more detail to certain things. I'm going to give you some hints. For example, we have not yet covered the stack and how to use the stack. We will be covering that today because the stack is quite an important part in the Amiga OS. So, as I said, also he's mentioning it here, okay? Scene.txt. He is talking about, let's say, those that want to understand how the demo scene works. I mean, he wrote it in 1996. At that time, and certain things that you needed to know, you can read the text. The text is very easily to put it in Google and translate it and read it out. It's quite an easy thing to do. It's just a text, so very easy to convert and read it in Google to understand what he's doing. As I was saying, and as I've been always saying, you do not need to understand the Italian that is in this book. You just need to understand the code. The rest, I'm explaining it in English. So with my, let's say, translation in English and with the code doesn't change, whatever language we use. You should be able to understand what there is. I'm just having the book open in front of me because of my notes. And because I am making sure that my notes are in point form and are something that I understand. It's not that I can give them to you guys and you will understand them. You won't. If they are incomplete sentences, etc. But it is one of those things for me to mark where I am, basically, more than anything else. So our code, okay, in all the examples till chapter 7, we had some initialization routine, then we called our routines, and then we had some closing routine, okay? That's how it all, this part of the code, you have seen it many times, okay? I'm not going to explain it. Well, I've explained it a million times now, but we always had this block, then our routines, and then the end block. With the startup file, we're going to eliminate these by hiding them in a way so that we just concentrate on our routines. That's what he said, what we are going to do. The above was the minimum what we needed to, you know, access the Amiga, but it was a very crude way of what we were doing, okay? With the startup file that he's going to show us, he's going to go into the detail of how we should have a proper startup file and access the Amiga hardware properly by calling the Amiga OS routines. Before we were doing it practically hardware wise, but that was very crude. Like this, the code, whether we use Kickstart 1.2 or whether we use Kickstart 3.1, because till 3.1 I think this is guaranteed, the code, the startup file, it will work either 3.0 or 3.1. I think it's still 3.1 because the Amiga 1200 had the 3.1 update very quickly. It's only 3.14 came at a later date, but till 3.1 it should be covered. Also because this book was also updated in 2016 when it was public and when it was published and printed, so there were some adjustments to it, so I'm assuming that was fixed. The first thing that we are going to come across is saving the what he's calling the workbench view, okay, WB view, okay, which is offset from GFX base 22. You can see it here. We were doing this, but we were doing it in a very crude way. So I was saying that we were accessing this in a crude way, this number 22 via A6, very in a very crude way, basically. Now we are going to use the OS way, which is through the load view, okay? Notice that here in line 4 we have sub a.l, a1 comma a1. That is we are making sure that a1 is 0, okay? That is quicker from CLR as far as I know. Many use the sub instead of the CLR to clear a register. Just to show you what I'm talking about, let's go to the browser. So we are in the graphics library, okay? So we go to the graphics doc, okay? You have links to this, okay? So don't tell me you do not know how to access the Amiga reference manual documentation, okay? You go to graphics and we check for load view, which is here, okay? Here is what load view does, Okay, basically it's a refresh. Okay, what we are used to in Windows F5 refresh, it's the same thing. We are doing a refresh of the screen to make sure that everything is fine. Notice also that A1 is one of the parameters that load view needs, but down here is saying if it's a null, okay, nothing is displayed, but it means it's going to do a refresh. Okay, so that's what we are doing. We are making sure that the screen is okay before we start taking notes of what there is on the screen. Let's jump back to the book. Here he is explaining that load view requires that you pass the structure of a view into A1. If you pass 0, it's a null, you reset the display, basically. You just do a refresh. The reset works for whether we are to have a low res screen, high res screen, Intel res screen, whatever. Okay, it does it. Like this, we also make sure that our couple list is refreshed. Now, before we start taking notes, the couple list is okay. Okay, there are no issues with it. That's why we do. That's why we do this this command, or we call this API. Like here, we are storing the web view, okay, port into this memory address. Here we are restoring it back. Okay, we are loading it into A1. We are loading the GFX base into A6, and we are calling load view with our A1, which points to our screen before we tell the system we want it. Okay, we are just setting up right now. Now, on the book, there is an error there in the comments, and even here. This should be wait top of frame, TOF, not wait off. Okay. What he does is we wait at the top of the screen when we when we do a refresh, so that we make sure that the whole screen is refreshed, not part of it. Okay. Another curiosity is that he used wait top of frame twice. Okay, I'm not sure if anyone can guess why he is doing it twice, but the reason why he's doing it twice is because of an interlace screen. Remember, interlace works, it scans the even lines. When it reaches the bottom, it does the odd lines, or vice versa. I cannot remember which one is which one comes first. I think it's the even first and then the odd. So he makes sure that we call wait top of frame twice, okay, to cover for this let's say anomaly, in case we are on a screen that is using interlace. I'm going to jump to my whiteboard. That is my whiteboard. This is something that I did quickly yesterday. In a normal screen, okay, we have 256 lines, okay, raster lines, I mean. You can see them with this color. I know the lines are not straight, but you know, please forgive me, I have arthritis in my hand, so it's impossible to do straight lines. So when we have a normal screen, not interlace screen, we are just doing the magenta lines, and top of frame is up here. We have 256 lines. We wait for top of frame, and then we refresh the screen. When we have interlace, we have 512 lines on the screen. Okay? Because of that, we need to do wait top of frame twice. Like that, we refresh the screen twice, and we make sure that we are on both raster lines, odd and even, basically, or even and dot. Now, we'll jump a bit to the browser. As you see, it's called wait top of frame, wait TOF, okay, not wait off, okay. And as you see, it says wait for the top of the next video frame. So it waits for when the scan line is at the first line on the screen, when it's starting up, basically, to draw the screen, and which you can call it also vertical blank. And that's when it refreshes the screen. Let's return back to the book. If you have any questions, guys, ask, okay? Or come to Discord. So, another thing, okay, which somebody yesterday, I forgot who, told me to translate these, you know, the wait top of frame in Italian. Do not do that. Not said it. I forgot how it started, but somebody mentioned it, and don't do it. Okay, learn the APIs of the Amiga with their real name, with what they are. They are in English, unfortunately, if you are Italian, and you need to know them in English, okay? Further down the line, you will not use minus $1 OE, but you will use wait top of frame, okay? Hence, do not try to translate them. Okay, so I just have a note that there is a mistake there, but I said it. So, to be sure, okay, we will add, so this was the opposite of, sorry, this was on entry, this is on exit. We improved the exit, okay? Sorry, we improved the, yes, we improved the exit. We are going to improve the entry. So basically we added, this is the difference between this code and this code up here, okay? We added the wait top of frame, okay? Also for when we are starting our code. Now, the GFX library takes care of our screens. As you all know, the Amiga has got Windows, has got a windowing system, okay? Before Windows was invented, we need to call the intuition library, and we need to use the API or method or function called rethink display, which redraws our windows on the screen and make sure that all is fine. The previous one only loads refreshes the screen, not the windows. They are separate things, okay? screens and windows on the Amiga are a different thing. On Windows 10, there is only Windows. There are no screens. Okay, just to give you the analogy. Okay, and as far as I know, no other OS has got screens and windows. There is only Windows. No other OS that I know. I mean, I'm talking to Linux or Mac or Windows 10. As far as I know, they do not have screens. They just have windows. The Amiga had screens and can have multiple screens. Okay. Um, okay. Somebody might tell me, okay, that you can have multiple desktops. It's not the same. Okay. On the Amiga, you can have both um, two screens of different resolution if you want to on the same screen, on the same display. That is not the same as what Windows 10 or Linux or that doesn't exist. Okay, so just keep that in mind. Okay, that screens and windows on the Amiga OS, they were different than as we know them today. So the graphics library refreshed the screen. The Intuition library is refreshing the windows. Do you rethink display? That's what it's doing. As you see, we are getting the intuition base. We do a check. If we do not get the intuition base, there's an exit. I will talk about this exit at a later time in a minute. I mean, not in a minute, but a few later on. But notice that there's that exit, okay? So if it fails, we exit. That's all you need to know. We do the same thing, not just with intuition, we also do it with the GFX base. If we succeed to open the library, then we can call our routine, our API. I'm going to go to show you the rethink display. Okay, so let's go to the browser. We are in, we need to go to intuition, rethink display. Okay, basically it gives us grant manipulation of the entire intuition display, but what actually it gives us is it makes sure, okay, that the Windows system on our screen is fine. We are not going to manipulate anything. We are just making sure that everything is working as it should. You see, that's what it does. That's the first thing. Okay, this function performs intuition global display reconstruction. Okay, and then it continues saying rethinking about all of the viewports, and viewports are windows. Okay, and their relationship to one to the other. Okay, so we don't have anything that is corrupted on the screen. Okay, so let's go back to the book. Let me see what note I have here. Okay, these codes, these libraries codes that we are using, okay, as I said, these are helping us making sure that when we take control of the Amiga, we are more accurate. We are less of having mistakes, okay? Till now, we have not discussed the blitter, and the blitter is actually in the next chapter. However, we do need to think about the blitter in our startup code, okay? So we need to make sure that we can take control of the blitter. And we also need to make sure that the OS is not using the blitter when we take control of it. Okay? And for that, there is some API call that we can use, or some Amiga library function that we can call. Okay? To be honest, 30 years ago, I would have said Amiga library function call. Now, I did not know what APIs are. Now I'm calling them APIs. However, I think the correct term is function, no? I don't know what is best to call them right now. It's just methods, functions, whatever one feels comfortable in calling them. So here is the first routine. Okay, JSR on blitter. Okay, that means we want the blitter for ourselves, nobody else. It's just us. We don't care about anyone else. It's us, and nobody can take it till we say you can take it. So we call this function. Okay, in previous code we could have still used the blitter. I'm not saying that you need by force to call it. Yeah, libraries is one library, but then you have lots of functions in each library. So what you call it? Function, API, what you call it? Method, I don't know. In the old days it was called function. Library is a group of functions. And API is a group of functions also, or methods. It's just that sometimes the term is swapped. I don't know. I'm not going into the technical details of this, but I'm just using the word so that people can understand me, unless somebody wants to tell me you should use that. And still, I will use what makes me comfortable, to be honest. But yeah, as long as you understand me, it doesn't matter. So on blitter, okay, let's go to the browser. By the way, the text can be seen, can be read, no? It's not that it's not readable. I mean, I did zoom before I started the text. So we are in the graphics library. So we need to go to the graphics library and then on blitter. Get the blitter for private usage. Okay. If the blitter is available, return immediately with the blitter locked for our exclusiveness. If not, okay, we wait basically. Okay, this is the proper way of taking control of the blitter. Before we were just saying, hey, we don't care, we just take it. This gives us better control. Although we have never used the blitter before, but if we had to use it, this is what would have happened. We would have just we wouldn't have cared, and we would have taken control of the blitter. Then when you exit, sometimes you get a screen corrupted. That's because most of these functions were not called. Okay, that's why sometimes you run a demo, and when you exit from it, or when you run it, you get a corrupted screen. It's because most of the time, I believe, is the blitter. The blitter was being used by the OS, and of course you didn't get exclusiveness to it. There are other things like not using proper fast mem and all that stuff, but depleter is also another thing that can cause a corrupted display. And you will learn later on why depleter can cause a corrupted display. It has to do with timings. I will cover that next week. Timings. So this is what onBlitter does. Okay, we return back to our book, and we have the opposite of onBlitter, okay, which is disonBlitter. We return the blitter to the OS. I'm not going to go to the book. It's. I mean, you already know how to go to the book and how to find the APIs, etc. But as you can see now, what we covered in chapter 3, because I covered how to look up libraries related to the Amiga and how to use the methods, etc. in that chapter, okay, in chapter 3. Okay, so we covered the blitter, how we take control of it, okay, and return it to the OS. Now, this is something that I think in chapter 3 also I explained, and I said if you disable the interrupts, there is no more OS, there is no multitasking. It is true, but it's a very, very rough way of taking control of the OS. Okay, the OS is nice to us. Okay, it provides us with functions that we can tell it, okay, we are going to disable you. Okay, so we are preparing you to be disabled. Okay, because of that, we have already covered disabled and enable. Okay, this is disable the interrupts, okay, which you see here. Okay, we have already use this one, disable and enable. Okay, we have already used these two, but there's another method which is called forbid, okay, which is disable multitasking. So we disable the multitasking the right way, and then we disable the interrupts. Okay, that's the proper way of taking control of the OS, not just by disabling the interrupts as we were doing. So on entry, we disable the multitasking, we disable the interrupts, and then on exit, we enable the interrupts and we enable the multitasking. Like this, okay, the Amiga will thank us and will, let's say, protest less by giving us less guru meditation. Okay, I hope this makes sense. I know I'm talking a lot today, and I'm going to talk a lot even in the next one, but it's theory that you need to know. So although he said in the beginning of this chapter that we are going to go deeper into the 68,000, we are going deeper also into the OS, not just the 68,000. So the title there is a bit misleading because he only mentioned 68,000, but actually we are going deeper into the OS too. And we arrive, so we are still talking about our startup file, but we are going to touch another topic, okay, the topic of the stack. Okay, we are going to talk how to use the stack on the Amiga and how it works and why it works like that and what different ways we can use it, although I will suggest not to use them, at least for now. So you all know that the registers on the Amiga are D0 to D7 and 80 to A7. Okay, but if you recall, some time ago I always said do not use register A7 because it's the stack. Register A7 is the stack, and if you use it, the Amiga will go haywire, will go crazy, completely crazy. So do not mess with that register A7. Register A7 is also known as SP. Okay, you can see it here. Okay, hold on. Okay, we are on the book. Okay, and I was explaining the blitter, and now I jump to this paragraph. Okay, so you didn't lose anything by me not switching, but I'm talking about this now. Okay, register A7 or SP. Okay, they are the same. The assembler will know that if you use A7, you mean stack pointer, and if you use SP, you still mean A7 or stack pointer. We have not yet devised a method of how to save the registers and the address registers. The stack pointer, the stack, gives us that flexibility of saving the registers to the stack. Okay? We have avoided the stack, but from now on we won't. And it becomes an important thing that we know how it works. Please note, I'm repeating this so that you bear with me, okay? Please note, we are covering this stack, but we are covering it because we are building a startup file, okay? So what we are going to learn for the stack, okay, is reflected in the startup file, okay? Now, using address register indirect, okay, we were able, okay, to, let's say if we move the bit plane pointer into 80, okay, then we can move a number, okay, into 80. 80 is incremented by 4. Remember here, this is long. And then we move another number into 80, and 80 is incremented by 4. In the same method, using the same way, okay, register address indirect, okay, we can do, okay, get what is in 80 and store it in the 0. Same thing, what is in 80 in the 1. Of course, notice that there's a minus, so we decrement -4, move the value, which we get 4, 5, 6, and we move it into the 0. And same thing happens for the 1. So 4, 5, 6 is in the 0, 1, 2, 3 is in the 1. This means that the last number in, okay, in this part, that was the last number, is always the first number out. Okay, last in, first out. Okay, LIFO. That's what it's called. Not FIFO, not first in, first out, last in, first out. Why we are covering this? It's quite related to the stack, but I'm just going to go a step further. So just notice what is happening here. Okay, we move something to an address, we are storing it, and we're storing another number, and it continues increasing. So 80 is incrementing upwards, okay? This word upwards is important. 80 is moving up towards the end of the memory, okay? And here is moving towards the lower part of the memory, okay? So there's that relation. Basically, I said what in both paragraphs, I just said what he was saying. And he is saying we are incrementing towards the end of the memory, okay? If this was 0, 0 is incrementing, and somewhere here is where we end without memory, okay? Now, a bit of history. This tech works, as I was saying, last in, first out. Okay? So, for that, I'm going to jump to my slides, whiteboard. Imagine, okay, imagine we have a pile of plates, okay? The first plate, actually, let's be here. The first plate is here, okay? The second plate is here, and we continue like this. The last plate, if we want to clean them, okay, let's say this is a pile of plates that needs to be washed. So the last plate on top, okay, will be the first one to be washed, okay? And we continue that till we reach the bottom. So all those that were pushed, let's say, to the stack, pushed to the, I'm using the term like in 6502, pushed. In 68,000 is move, but right now I'm using the word push. So we are putting plates one on top of the other, okay? When we are washing them, okay, we are taking the top one out, okay, always. So we are pushing and we are pulling. And remember, it is last in, first out. Imagine another scenario, okay, where we have the comics, okay, where we have comic 1, we are reading a series of comics from 1 to 50, okay? We read the first one, then we read the second one, the third one, and we continue going like this till 50. Once we read them all, 50 is on top, okay? If we need to sort them out or arrange them, then we need to start moving from the top, okay, and piling them the opposite way around, okay, so that we can have one on top again. So we can go to 1 again. Same principle, okay? Just notice that it works with this principle, last in, first out. Let's return back to the book. So, a bit of history. When the first computers were designed, okay, we had they had a certain amount of memory like today, okay? So let's say this is the start of the memory and somewhere here is the end of the memory, whatever that was, okay? Let's say we start at 0 and we end at 100, okay? Just to make it simple. The programs started at 0 and incremented towards the 100, okay? This tech was the opposite way around. It started at 100, okay, and decremented towards the 0. Why was this method used? It was used because like that the program will not conflict with the stack, or when it conflicts, it will be at a lot later date, and it's very far, and because it was far away, it was considered it will take time till it can conflict with the stack. In today's modern CPUs, the stack is protected, no? But in the old days, in the beginning, the first CPUs, that was not. Now, why I'm saying this, okay? The reason being is that here we were simulating the stack, but the memory was growing upwards, okay? And then when we take from the stack, it was growing downwards. In this scenario, it goes downwards when we are putting things on the stack, and it grows upwards when we are taking things off the stack. Okay, so that is why we go into the history of it. The 68,000 is no different, okay? The stack goes from top to bottom, okay? It doesn't mean that it's at the end of the memory, don't get me wrong, like the old system, but it works on the same principle, okay? It starts at an address and it goes lower towards the 0. And then when we take things out from it, okay, when we pull things out, then it goes up again. So same principle, just it doesn't need to be at the end of the memory. Normally, the stack is managed by the CPU and the OS, okay? This is quite true, especially in a multitasking operating system. The stack is crucial. However, because we are taking control of the Amiga, we have better control, okay? But still, we need to store things. We still need to preserve the registers, okay? And then return them back. That's why we need to know these things. Here's an example of how we write one register to the stack. So we do move.l did 0 and then minus to the stack. So register address indirect, but either A7 or SP, okay? We could have had A7 there instead of SP, and we would see basically the same effect. It would assemble in the same thing. Okay, we moved the contents of the 0 when we did the move long to the stack. So 4 bytes of the stack were populated and then the stack pointer was decremented, okay, first, and then 4 bytes were populated. The opposite way happens, okay? We get something from the stack, okay, and then we move it into the 0. So we get what was on the stack, and then the pointer is incremented, okay? He says here what I just said, that SP and A7 are the same, okay? Okay, now here we have another example of moving lots of registers to the stack. Notice we are moving, okay, the 0, the 1, the 2, the 3. And the stack has got a minus, okay? So we are moving to the stack. When we want to take out of the stack, okay, we have a plus, okay, with the register A7 or SP. Also notice the last one out, the last one on the stack was D3. So we get back D3, then D2, then D1, then D0, okay? That's how it works. As you can see from his diagram, simple diagram, by using, when we are putting things on the stack, we are using the minus SP. When we are pulling things, we are using the SP plus, okay? Here he mentions the same thing that I mentioned earlier when you have a pile of comics, okay? You start reading with number 1, and when you end up all the comics, you end up with number 50, okay? So 50 is on top. If you want to go back to number 1, you have to go through all the others. If we write to the stack, okay, and each time we need to specify, we know we have 16 registers, actually 15 because A7 we cannot use. We have 15 registers. That's still a lot. If we had to write them each time one by one, okay, that is a long way to go, okay, to store 15 registers. So there's a short way of doing it. If we want, ignore that there's a move M, not move, okay? I will come to that later. If we want to store the registers D0 to D7 and A0 to A6, we just write them like that with a dash in the middle, and then A0 and A6 with a dash in the middle. And to differentiate between address registers, data registers and address registers, we use the slash, okay, the // and like that we are writing all the registers to the stack pointer, of course without A7, and then we are getting them back in the same method, okay? So SP plus, and then D0 to A7, A0 to A6. I'm going to talk about move M. You do not need to write move M, okay? But move M is the actual instruction that moves the data registers or address registers to the stack. The assembler knows that we are moving to the stack. So whether we write move M or move, it's able to distinguish that, and it will translate it into a move M. Okay, that's done for us behind the scene. So you do not need to know the move M. You don't write it actually. It's good to know, but you don't really write it. So you always use the move. That's why in some cases, for other things also, we were able to, because there are other types of move, okay? We were able to disguise them because move can be interpreted, if you look at the 68,000 manual, okay? You will see that there's a lot of moves, move M, move P, I think. There's lots of different ones, but the assembler hides all these from us, okay? You just need to remember the word move, and it will assemble into the right instruction for us. Okay, so here is where he says what I just said about movem, and also about the way to specify the data and address registers. We just use the dash and the backslash to write them. Okay. Now here's a curiosity. Okay. Notice the first one, we're moving data to the stack. But the second one and third one, we are not moving data to the stack pointer. We are moving data to somewhere else in memory, whatever that pleases us. So in the 68,000, you can move the stack wherever you want, or you can have your own stack if you want to. But for now, please stay with the 68,000 stack, okay? Don't try to use other types of stack. That's quite an actually it's quite an advanced topic, and you don't really need to go into that detail, at least for now. But notice that we are moving all the registers to label, and or we are moving all the registers to location 53,000 hex. Okay, the same thing is we are reading back everything that was on the we were notice that we are moving back what was in 53,000 hex into the address register, into the data and address registers, same that was what was on label and same what was on the stack. Nothing changes. Okay, here notice also, guys, that I am skipping the text because I know that the examples is what you need to know to understand, because the text is what the examples are showing. Here we saw the shorthand to move all the registers to the stack pointer, but this and this is the same. Okay, notice there is no repetition of the same address. The assembler, I think, will get confused if you try to do it. The assembler will get confused if you try to do this. Now, we are using ASIM Pro, which is a descendant of ASIM 1. Okay? Notice what ASIM Pro or ASIM 1 is able to do. You do not need to use the slash. You can specify the dash. That only works in ASIM 1 or ASIM Pro. Okay? It doesn't work on other types of assembler. It's only able to be interpreted in ASIM Pro or ASIM 1. So avoid this if you want your code to be compatible with other assemblers. Here he's going to give us more examples. We have other ways of how to write when we want to move registers. Okay, so D0 to D2, we specify the dash. Because we are not copying D3 and D4, then we use a slash. Okay, then we copy D5 and then another slash because we are changing to another register, which is A3. Okay, here we have a different story. We are copying D2, but then D3 is not. Then we do D4 to D6, okay, and then A3 to A6. So notice when there's a change, not a sequence, we need to use this slash. And the same thing when we are getting it back, okay? So far, I think you have understood how movem works, and that movem and move are the same, okay? Notice and know that multitasking operating system use the stack all the time. They cannot function without the stack. Why? Simple. Once they start a task, they save the registers. They do the task and then they restore the registers. Then they jump to another task. They save the registers and restores them back. And it continues like this. So this is why this stack is important, that you understand how the stack works. This type of Ozzy, I'm reading your messages, but I will come back to you in a minute, okay? Just to finish what I'm doing. Notice that when we call a routine, okay, the best way to do is when we do a branch to subroutine, and let's say this is our routine, okay? we save the registers, we do something, okay, and then we restore the registers back and return back. This is what the OS does all the time, and this is what we will be doing also many times, okay? So keep it in mind, this from all the stuff that we covered, I think this is the part that you need to keep in mind all the time, okay? How to save the registers and restore them back, because you will be using this quite a bit. If we had to write a routine, okay, notice what we are doing in this one, okay? We move things to the stack, we move more stuff to this, we pull things from the stack, and then we pull things again from the stack. What do you think is going to happen? We passed the point where we actually save stuff, okay? Of course, the Amiga is going to go haywire here, okay? So you need to make sure that they are in sync. Whatever you save and restore, they are equal. Here we have 2 saves, 2 restores, okay? Not 1 save and 2 restores, okay? The Amiga will crash or will behave strangely. Probably it will give you software failure instead of hardware instead of Guru, but still it will complain. Now we have arrived to the actual startup file. As I said, this is not the complete startup file, okay? It's part of it is there, but there's part which we haven't covered, which is the heavy in it. What I was saying is that here is what I just covered basically. There are some things that I haven't covered yet, but I'm just going to talk about them in a minute. Here is where we save the GFX base. We save the intuition base, okay? And notice the exit. If we do not get access to the GFX base or the intuition base, we go and exit, okay? It's either we come here or we come here. Depends which one it is. Here is where I haven't covered this, but I'm going to say it. There's a routine, okay, where it permits us to reset the sprites. This will only work if you have Kickstart 3.0 and above. This method or function does not exist in lower Kickstarts, okay? So this is why you need to call the OS APIs to do this, okay? It will know and it will detect it and it will either do it or it will not do it. Here is where we are saving the workbench view, but also doing the wait top of frame, okay, for whether we have interlaced or not. Here we haven't covered this, but I'm going to mention it. Remember, each OS, even Windows today, each task, okay, in Windows, in Linux, in Mac OS, tasks has got priorities. Same is the Amiga OS. It gives priority to tasks. Okay, so we are telling it that our task needs to be the highest task, the most fast task. Okay, we need to have the highest priority. That's what we are telling the OS here. Why we are doing this? It's very simple. Okay, so we no matter what happens, we are always the fastest. We don't want anyone to interrupt us, and we do that. Here is the wait blit. and on blit. Wait blit I haven't covered, but it's further down. Basically, on blit is telling that we want to take control of the blitter. Wait blit is we make sure, you know, that the blitter finishes what it's doing, and then we can take control of it. And he caused it twice with the same issue if we are using interlace or not, just to be sure. Okay. Here we have the for bit, which disables the multitasking, and the disable interrupts. Okay. As I said, we haven't covered this part, so we will not do that. But we have arrived at, now we are returning back to the OS. So we enable interrupts, then enable multitasking. Okay. We set the task, okay, to normal or whatever. We're going to kill our task anyway. We return the blitter. Okay. We give the blitter back to the OS basically, and then we restore the copper jump. Now you are going, for those that have got actually I skipped part, we also reset the sprites. We return the sprites to what they were, but here there is something that we haven't talked about, we haven't mentioned, but those that has got sharp eyes will notice it. We have always talked about the copper jump, okay, and we mentioned that there is copper jump 1, there is also copper jump 2. Okay, we have not used it. We are just making sure that if the OS is using the second jump, we also return it, or we also set it in the right way. This is why we are taking care of it. In future, you're going to see how we can use the second copper list jump address. The rest is closing the libraries and returning back to the OS. It's the same code that I explained earlier, just not it was in shorter blocks than here the whole file together. Notice also when we are returning back to the OS, we are restoring the registers, okay, as they were in the OS when we left it. Okay, so this is really the right way and the clean way of how we take control of the OS and then returning things back to the OS. The heavyweight, okay, I can give you some tips, is related to the screens and stuff that we create, okay, which we will cover not today, at a later date, probably next week. However, before we even cover the heavy in it, I'm going to give you a hint for next week. You need to understand timings. You need to understand DMAs, okay, and which DMA takes priority over which, and all that stuff, and what is their timings, and where they happen on the raster line, and all that stuff. This is now getting into the detail of how the Amiga really works, okay? You need to know a raster line, what happens on the raster line, and what is in control of the raster line at that moment in time. That's how deep the book goes. By the way, these timings and stuff that I'm mentioning are also in the Amiga hardware reference manual, but they are not as clear as Fabio mentions them. We will not cover them today, unfortunately, because this chapter is quite a long chapter. I think it's 30 pages by itself. And today, I mean, I don't know which page are we. Yeah, we we did about 10 pages, so at least 3 streams to do all the chapter. Depending on the exercise, because the exercises, we haven't done any exercise, but there are quite a bit of exercises. And there's also lots of exercises that I edit to what there is. So this paragraph, he's saying, okay, that what we need to note, or that he hasn't covered, is that we do some tests for when we open the graphics library and intuition library. Okay, so I did cover that. Line 90, okay, and earlier, okay, we are using the copper jump 2, okay, or cop 2 location. It's called cop jump 2 normally. Here it's cop 2 LC. It's the same thing. So that is something that we have not covered. Also, we haven't covered, but he mentions it here, how we are testing for the sprites and resetting them if we are on OS 3 and above. Also, we are, okay, in this paragraph, he continues to talk about the priority. So we take control, tasks has got priorities. We set our priority, which is the maximum. And then when we return to the OS, we are returning that back to what it should be. So we are basically thinking of everything that there could be on the Amiga before we do anything. Now, what you need to imagine, okay, so far you haven't seen any source, but what will happen is we will have like an include at the top of the source. We'll have something like include startup file, okay, startup.s or .asm, whatever. Then our code will start with something like main. We'll have a label called main, and our code will start. When it does, when we hits an RTS, it will return back to the include file, okay, the startup file, and it will do the return to the OS. I cannot stress, and I've repeated many times now in today's lesson, you cannot continue to follow me without having the sources. Go and download the sources. You will need to see them. The listings are quite long. Before, I could divide them in blocks, but now there will be blocks that will be hidden because they will be in include files. Okay, so even the book will not show those. Okay, and sometimes you will need to look at those. So please do that. Just to give you heads up, next topic is DMAs, and he covers DMAs here. We will not be covering DMAs. This is where practically I finished yesterday. I hope you enjoyed this lesson. It will be a lot like this, and the topics will be very advanced now. So see you next week. Thank you guys. Bye bye.